Topic of today's class is transport phenomena in perfect gases. The equilibrium state of any gas is most probable state, but if the gas is not in an equilibrium state, then there are following three cases. First one is if different parts of the gas may have different velocities, then there is relative motion between the layers of the gases with respect to one another. In such cases, the layers moving faster may impart momentum to the slower moving layers to bring the gas into equilibrium state. This gives rise to phenomena of viscosity. Other case may be if the different part of gas may have different temperatures, then the molecules of the gas will carry kinetic energy from regions of higher temperature to lower temperature, and this will give rise to the phenomena of conduction. One more case arise if the different part of the gas may have different molecular concentration, then the molecules of the gas will carry mass from regions of higher concentration to the region of lower concentration, and this will give rise to the phenomena of diffusion. Thus, the phenomena of viscosity, conduction, and diffusion represent the transportation of momentum, energy, and mass respectively, and these phenomena are known as transport phenomena in perfect gases. We have been able to quite relate few macroscopic properties of gases such as pressure, volume, temperature to molecular behavior on micro scale. We saw how macroscopic pressure is related to the molecular motion in perfect gases. These three different transport phenomena like diffusion, thermal conduction, and viscosity are described by their corresponding coefficients such as d for diffusion, k for thermal conduction, and eta for viscosity. In diffusion process, molecular transport due to concentration gradients is discussed. Thermal conduction is due to the transport of energy, and viscosity is due to the transport of momentum. First, before starting these transport phenomena, first we discuss about mean free path, because this is the main component of discussing the formulas for transport phenomena. In order to consider the diffusion, we must first look in details at molecular collision. And here we suppose that all molecules are same and collide elastically, and also suppose sigma to be an effective molecular diameter of the molecules. We will follow the progress of single molecule as it collides with other moving through the gas as depicted in this diagram. For simplicity, we assume that the rest of the molecules are frozen in their positions. Thus, if our lonely molecule travel distance L, it will sweep an element of volume pi sigma square L, where sigma is the diameter, and if there are n molecules per meter cube, then our molecule will collide with pi sigma square Ln of them. We can see in this diagram also, we can now define the mean distance between collisions or mean free path as distance traveled divided by the number of collision. So distance traveled here is L, and the number of collision is n times pi sigma square L, which can be written in the terms of Boltzmann constant as kBt upon p pi sigma square. We only consider the simplest approach. In reality, other molecules are also moving, because there is no only single molecule moving in the gas. So, if the speed distribution will be described by that of the Maxwell distribution of speed, as we have already discussed in earlier classes. From there, we can get the expression for probability in this way, where lambda is 1 upon root 2 pi sigma square n. We see that lambda is proportional to 1 by n, and which is also proportional to 1 by p. For air at standard temperature and pressure, lambda is around 100 nanometer, while the mean distance between the molecules is of the order of 3 nanometer. Number of collisions per unit area per second, which we call as flux. Consider a volume of gas with concentration n and mean velocity v, and let's see how many molecules will pass through an area A per unit time. This is also known as cross-sectional area. We further split our velocity in three components, as we have three directions x, y, and z, one of which is perpendicular to the area A. Then in time t, about 1 by 6 of the molecules in volume V T into A will pass through A, and hence flux is given by 1 by 6 of an average velocity. A is the area times T divided by area times T, which will come out to be 1 by 6 n V bar. This is the flux which comes through, which define as number of collision per unit area per second. So here first we will discuss the process of diffusion, the transport phenomena diffusion. If we consider gas with a concentration gradient, it should be clear that molecules will move from the more concentrated to the less concentrated region by a process of collision, or we can say random walk. This is diffusion process. If we consider that over a distance dx, concentration change is dn, the concentration gradient is defined as dn by dx. The number of molecules crossing area A normal to gradient per second can be then written as dn over dt equal to minus d, where d is the coefficient of diffusion, dn over dx is the concentration gradient multiplied by the area A. This is also known as Fick's law, where d is coefficient of self diffusion, and negative sign implies here that the flow is in the direction of a smaller concentration, because molecules move from higher concentration to a smaller concentration. This is the diagram. Here we depicted the layers, layer 1, layer 2 and layer 3. The distance between two layers is lambda, and this is the concentration at first layer. It is n plus dn over dx into lambda. This is higher concentrated layer, and 3 is the lower concentrated layer. We would then have the number of molecules per second crossing from layer 1. It is given by 1 by 6 b bar A, which is the flux, which is our flux, multiplied by the concentration, that is n plus dn over dx lambda. Similarly, for layer 3, it is 1 by 6 b bar A times n minus dn over dx lambda. There will also be molecules leaving on each side of 2, because some molecules are going from 1 to 3 and some are going from 3 to A. So the net transfer is given by the subtraction of this whole expression, and we get as minus d dn over dx A. This is trivial mathematics here. For air at standard temperature and pressure, sigma is 0.3 nanometer, lambda is around 100 nanometer, and velocity of air is around 450 meter per second, which we have taken as parameter here. And n is number of molecules is around 3 into 10 to the power 25 per meter cube. With this, if we calculate the coefficient of diffusion, then it comes out to be the order of 10 to the power minus 2 meter square per second. Hence, D can be related to macroscopic temperature and also pressure, and V through the number of molecules. In this diagram, we can see that if L is the distance traveled, then difference from the previous consideration is that now N is x times T. Here we have also taken the dependence of temperature, and dn over dt is not equal to 0. So we have another relation, which is dn over dt equals to d into d2n over dx square, where d2n over dx square is the second derivative of the concentration gradient. From here we can find, if we solve this equation with the help of differential calculus, then we find that n is equal to n naught upon a pi dt square root times e to the power minus x square upon 4 dt, where L is very very large than the diffusion constant. N0 is the initial number of molecules and A is the area across which gas expands. So now we will discuss the thermal conductivity, which is due to the transport of energy. Here also we are considering three different layers. The concentration at layer 1 is higher as compared to the layer 3, and if T is T is the thermal conductivity, T is energy, then it is T plus dt over dx times lambda, and at layer 3 it is T minus dt over dx. Mean free path between two layers is lambda. we define the heat as minus K. This expression we have already worked out in earlier class. And this Q equals to minus Ka dt over dx, where K is the thermal conductivity and Q is the heat energy. Now the rate of transport is, this time, is dq equal to Cv over dt, and we have already a flux factor 1 by 6 Nv bar, which we have already calculated in earlier slides. So the net transfer at the layer 2 from 1 to 3 and 3 to 2 is around 1 by 3 Nv bar. A is the area, Cv is the specific heat at constant volume, dt over dx is the temperature gradient, and lambda is the mean free path. With the help of this, we can calculate the coefficient of thermal conduction is equal to 1 by 3 Nv bar lambda Cv. Now comes viscosity. This is due to the transfer of momentum. Here, if there are two layers, then I have already discussed that there is relative motion between the two layers. So on the upper layer, or with the or the layer having higher momentum, there is a drag force F applied to maintain constant flow, which is proportional to eta A du over dx, where eta is the coefficient of viscosity. We further assume here that u is less than v. The only molecules reaching 2 are those that just made their collision at distance lambda, because we have considered that the lambda is the mean free path between the two layers. Thus, the number of molecules crossing A is 1 by 6 Nv bar A per second, and from 3 this molecule bring to 2 net horizontal momentum. So we have two expressions, one for layer 1 and one for layer 2. Layer 3 and layer 1. Layer 3, it is m times u minus du over dx lambda, Nb bar over 6 is our flux, and A is the area. Similarly, from 1 to 2, it is m u plus du over dx times lambda, Nb bar over 6 into A. But 2 sends 1 by 6 Nb bar A both ways. Thus, the total momentum transfer per second is F equal to m lambda Nb bar over 3 multiplied by area multiplied by the gradient. With this, we can find out that eta equals to 1 by 3 mv bar upon pi sigma square. We can also discuss here when these are the three different phenomena of transport, but if there are charge also, then there is one more phenomena. This is called as electrical conductivity. We all know that from our previous expression, this expression is used in 12th class physics also in the electric field part. Electric field is defined as the voltage difference divided by the length of a conductor. This ratio comes out to be constant for a particular voltage. A charge E is subject to constant E experiences a constant force F, which is equal to ma. Force is also defined as mass times acceleration, and the drift velocity is then given by v equal to at, which is given by ev upon ml from this expression in times t, and grows linearly with time because v is directly proportional to t. Now let us consider that a collision takes from v equal to 0 to vt for time t, then b bar is 1 by 2 eb upon ml, where eb upon ml times t is velocity, and average out, we have taken average of this, so we divided by multiplied by 1 by 2. So the current density comes out to be, this is very familiar expression for current density, J equal to E N B bar, and by putting these values we find out that the coefficient of electrical conductivity, this is sigma, equals to E square N Tc upon 2m. So this is for today's class, and from the numerical for this part we will discuss in next class. Thank you.